This is K8BYP, not a ham radio video necessarily, but an automotive video, and we all have vehicles. And this video, or perhaps two, are about engineering details, applications, and correct ways to install mainly radial ball bearings like these. You might find some small inch series bearings a bit smaller than that in some radio equipment, maybe on a VFO shaft. But this is the rotor and the rear cover from a GM alternator off my 1995 Chevy S10 pickup truck. And it's failed at least 5 years sooner than it should. And from looking at the commutator, see, the front commutator ring has no noticeable wear on it. The back one's significantly chewed up. Why? I thought this vehicle had a bad belt. I was hearing an occasional chirp. I took the belt off, spun the alternator pulley, and I heard a squeal in the back. And this rear bearing was bad. So that bearing was in a place where I could not get behind it to pull. So I had to disassemble the bearing, cut the inner race, and pry it off the shaft. And you can see where I cut into the shaft a little bit. What's happened is that when they designed this alternator, now this is the front cover, but the back cover is similar. On the back cover, they did not cover over where that bearing is. And water and debris got in through the bearing seal, which is that red kind of brown looking rubber thing, flat. Water got in. It was an old, new, remanufactured surplus alternator, which was probably 5 years old when I got it in about 2013. And you can tell by the commutator, there's almost no mileage put on this vehicle. So that bearing shouldn't have failed. But water got in the seal and damaged the bearing. The water and debris went through the bearing and got in between the brush and the commutator ring on the rear of the commutator assembly and damaged the commutator surface. That's fairly easy to fix by putting this rotor in the front housing and the bearing and spinning it with a flat file against the commutator to file down the ridges. That's the reason the bearing failed. The bearing was properly installed, but the application wasn't correct because it was exposed to water and debris. And that's one of the original seals from the bearing. To understand how to correctly install these bearings and understand why they are in certain ways extremely fragile, we have to understand how they're designed and how they work. These are deep groove radial ball bearings. This bearing might take 800 pounds load this direction. It can only take maybe 150 pounds axially or this direction. If you need a bearing with the ability to carry more axial load, there's a different kind of ball bearing for that. I'm going to show you how to remove the seal, hopefully without damage. We get a sharp dental pick. We reach under the outer race and we lift up carefully, and pry that seal up. And we can see inside the old grease is dry. So the oil in the grease has leaked out over the years, and that bearing's going to fail. Inside the bearing are 1, 2, 3, 4, 5, 6, 7 spherical steel balls. We can't see them because of the retainer, the stamped retainer that's riveted on each side of the bearing balls to keep them in position. There on the top right, you can see part of one of the bearing balls. With the seals removed, if we pick up a new bearing or a bearing that's had the grease cleaned out, we shake it and the whole thing's loose, and we think, well, there's a lot of clearance. Well, there isn't. When these two races are aligned exactly correctly, the clearance between the ball and the race might be on the order of 5 to maybe 120 microns, millionths of a meter. So that shows the need to properly install and operate these so that both races are in exact alignment. And what that means is that there can only be an interference fit on either the outer or inner race. And this is universally done wrong, and that's why these bearings fail. Since that clearance inside is extremely small, and those bearing balls are perfectly spherical, perfectly round, then when that ball presses down on the race, even with a few pounds force, there could be hundreds of pounds of pressure generated. I once did a calculation from Mark's handbook on a 1/4 inch ball on a perfectly flat plate with 2 pounds force applied to the top of the ball, and the resulting pressure was on the order of 2,000 psi, and that's because the contact area is almost zero. And since pressure equals force over area, even a small force under a very tiny area results in an extreme pressure. When these races are misaligned, especially by having an interference on both races, this bearing unit cannot align itself and it's going to wear out. The other thing is, do not even drop that bearing from that height on a table, especially on concrete. It'll be damaged. Because when it's dropped, that impact loading is going to multiply that force, and it can literally cause the bearing ball to put a dent in the race. Now, when the ball goes around, when the balls rotate around, you'll hear a thump, 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 thump. You drop one of these without insulation or packaging, throw it away. Do not use it. And it takes surprisingly little to do that. If you have some old stock bearings, they may have dried out grease. The oil may have leaked out. It's possible to pull these seals off, even a bearing that's assembled in a fixture, and wash the old grease out, spin it round, and put new grease in. There must be no contaminants in there because since the clearance is millionths of an inch, very small pieces of debris can get between the ball and the race and damage either one. And then once that's damaged, the continued operation is going to play grinder inside and chunk away and break off little pieces, which cause more damage. Damage runs away and destroys the bearing. Absolutely never mount that bearing in a housing like this. Absolutely never hit that inner race with anything, even a screwdriver handle, because that will cause permanent damage. That can generate tons of impulse force and dent that really hard bearing metal. It'll actually dent it because both metals are extremely hard. Bearing application. It's universally practiced to press bearings such as this inner race with a slice in it. It's common practice in mechanical and automotive to press that on the shaft, and that is the wrong thing to do. See that dark mark on the shaft? Now that shaft looks pretty clean because I polished it with 600 grit sandpaper. When that bearing inner race is fit on that shaft, there's supposed to be a negative clearance. The general rule is the member that rotates, either the shaft in this case, or if the housing rotates, then the race in contact with the moving member must be locked in place. That's generally done by a light press fit with small bearings like this. That inner race might have a negative clearance of half of a thousandths to maybe 2/1000ths of an inch. That's a light to medium fit. Why it's wrong to press bearings on. Firstly, without a very good machine shop, it's impossible to get the bearing started straight. That's going to cock the bearing sideways. The press force is going to gouge metal on the shaft because the bearing steel is much harder than the shaft. That's going to drag metal fragments in. Even pressing it on straight is going to cause the hard bearing material to scrape off pieces of that shaft. That's going to get embedded and make the bearing go on crooked. That's going to kill the bearing, shorten the life, because now the internal very close clearance is off because the one race or the other is trying to run crooked. In applications like automotive differentials, take the carrier or the pumpkin out. Notice there are shims inside down to the thousandths of an inch. Those bearings have to be shrink fit. In other words, heated to expand the inner race and dropped on the pumpkin, where it then cools and fits tightly on the shaft on the pumpkin. Else, pressing it on is going to drag metal ahead of that press on that inner race, and that metal is going to build up against the shims and going to cause a lot of excess clearance or lack of clearance one way or the other. And this is why mechanics universally have trouble with rebuilding differentials. They have to take bearings on and off causing damage to the shafts and the housing, and change shims. I've rebuilt 2 differentials in my life. I shrink fit the bearings where possible, and the result was a perfect fit, perfect alignment, and no need to change shims or the crush sleeve. So universal rule, the member that rotates here has a slight interference fit with the bearing. In some cases, like the front tapered roller bearing in an automotive differential, front means the front of the differential towards the drive shaft, that first tapered roller bearing is going to have a cup that fits inside the axle, and we can't heat the axle to expand it and put the cup in. So it has to be very carefully, the bore of the housing has to be carefully reconditioned, smooth, and the cup must be pressed in absolutely dead straight. And without taking the differential housing out of the vehicle, we can get hardened all-thread rod, hardened nuts and washers, and make a press to press things like that in without having to go to a machine shop. This is the front housing from this alternator, aluminum housing, steel bearing. This is a case that violates that convention because here, for the purpose of getting this unit assembled, the bearing is a slight interference fit in the housing, and the front of the shaft is a slight clearance fit in the bearing. That's wrong. That tends to cause, you can see some damage on that shaft. There's a failure mode in bearings called stick slip. That's a thing in friction, where occasionally a bearing might try to instantaneously seize and then let go. If that happens, the inertia of that big heavy rotor is going to continue to rotate that shaft, and the shaft will rotate inside the inner race of the bearing and cause damage. If that eventually locks up, it can seize the bearing up and cause severe damage to the housing. So to install this bearing, I took this front housing, which is only just an aluminum housing. There's no other rubber, other pieces fit to it, no electronics, no nothing. And I put it in the toaster oven in the kitchen at about 250 Fahrenheit and left it in there for 10 to 15 minutes. When materials like this housing heat, they undergo volumetric expansion. This outer diameter gets larger. The inner diameter where this bearing is gets larger. And for these small metric and inch series bearings, I found that about 250 Fahrenheit is more than necessary to expand this housing. I did that. I took this out of the oven. I set it down on an insulating surface. I picked the bearing up and dropped it, and the bearing literally fell all the way in and landed against the machine surface inside that housing, an absolutely perfect fit with no press damage. Now that was after I took 600 grit paper and polished out the inside of this housing bore so it's smooth. But to try to press that steel bearing in, there's going to be an edge there. It's going to be a little crooked. It's going to gouge metal up, and that bearing's going to go in crooked, and that will destroy the bearing. Once the housing cools, it then shrinks against the outer race of the bearing, and that's where the term shrink fit comes. You might commonly hear the term press fit, but again, that's the wrong way to do this because it will damage the housing. Unless we have a really good machine shop, and there's still going to be some damage from the friction of pressing that hard bearing in that soft aluminum. To install this new rear bearing on this shaft, we don't heat this because that's a complex assembly with copper wire. If we overheat this assembly, it's going to cause shorts in the wire because it's going to break down the insulation between the windings. So the practice here is to put the new bearing in the oven and heat it to about 2 to 250. And it should just slip right onto that shaft all the way in. Now when the heated, let's say the bearing is heated, the inner race is heated. When that contacts that cold shaft, where that contact is made, there'll be heat transfer, which begins to cool the inner race of the bearing. So the clearances start to decrease. So we've only got about half a second to get that bearing set all the way on, or it's going to shrink and grab onto the shaft, and then there's no choice but to press it on the rest of the way. Now for this bearing application, the distance that bearing is pressed on a shaft is not critical. It basically doesn't quite go up against the commutator. It can't touch the commutator ring because that'll short to the shaft. Now, unlike this front bearing, which is shrink fit into a metal housing, the rear bearing has a plastic compensation ring that the outer race fits into, and there's a slight clearance. That slight clearance is vital. It's mandatory so that when the bearing spins, it can self-align and carry the maximum load. So the rule is, for this small bearing, inner race shrink fit on the shaft, outer race needs maybe a half or a thousandth of an inch clearance so it can self-align. If it can't, the bearing will be destroyed. In applications like medium to heavy industry, this becomes a crisis. For bearings that are several inches to several feet in diameter, they're not made like this. They may be made with filling slots to be able to remove and install bearing balls because the outer race may be so heavy it takes a forklift to pick it up. So they might actually assemble the bearing in place. A bearing improperly installed by a mechanic who accidentally or deliberately hits a race to try to seat it and is damaged can cost an assembly or production line to go down. And that kind of downtime can be reckoned in thousands or tens of thousands of dollars a day in lost production. In industry, mechanics and technicians should actually be trained on this kind of thing, including failure diagnosis, what to listen for. For heavy industrial lines, there might be vibration monitors mounted on bearing pillow blocks or on near shafts to look for shaft run out or vibrations before a bearing fails and destroys a housing and shuts a production line down. In automotive, it's generally not that severe. If this alternator fails, we can probably drive a half hour with the lights off and maybe get someplace or get home before the battery discharges. But other bearings like axle bearings and especially universal joints are critical. Never, ever ignore the manual because it's wrong. Never, ever take a universal joint cup and press it in a drive shaft yoke. You will cause failure. Guaranteed. It is vital to cut universal joints apart, to press the caps inward because the inside of the cap from centrifugal force will catch water and rust. So the procedure that mechanics do to remove a U-joint by pressing the caps out is going to cause severe damage to the drive shaft yoke, which is generally softer cast iron. So the correct way to replace universal joints, which are not ball bearings, they're needle roller bearings, is to cut the old joint out and press the caps in, recondition the bores to just either a very slight interference or a very slight clearance. I set them to a slight clearance. And the caps should go in the universal joint or the drive shaft yoke or the yoke on the back of the transmission by finger. You should be able to push them in with your fingers. Some of the older GM applications actually had the caps put in with a clearance fit and then they injected nylon in to lock them. Which brings us to another critical point of these ball bearings. Ball bearings cannot tolerate frequent starts and stops. That's why drive shafts have needle bearings, because of frequent starts and stops and changes in velocity. Starting, stopping, and reversing will destroy this ball bearing, because what happens is called ball skidding, because the bearing balls cannot instantly start turning, so they slide a little bit when one or the other races begins to turn or stops. And that causes rubbing and damage to the races and the balls. So avoid frequent starts and stops. The grease inside these bearings tends to be heavy. This makes a case for warming vehicles up. Ignore the environmentalist hysteria about wasting fuel. It wastes very tiny amounts. And the downside is, even these bearings need to have some heat to soften the grease to distribute the oil. Don't start the vehicle up and suddenly go take hard corners and do aggressive driving with the water pump, drive shaft, rear differential. Give those units time for the oil or grease to distribute and maybe get a little bit of heat to thin the lube out. Because cold operation, jackrabbit starts, hard stops in vehicles just destroys bearings. There are three versions of ball bearings such as this. There's the open bearing, where we can see the internals. That's usually used inside an enclosure with oil or grease, no atmosphere exposure. These bearings are sealed with the orange seal there has a metal plate inside, and then rubber is molded around it. Notice the orange color there and the dark color here. Notice the brown there. And notice inside the brown, the seal lip is black. That's very important. The other versions of these are shielded with a metal cover and then sealed. Sealing has the option of contact or non-contact. If there's any moisture around, we want contact seals to keep the water out. For automotive applications like this is a proper front bearing from an alternator shop. Avoid going and getting common, inexpensive bearings. The reason I put this bearing in with the orange colored seal is that orange is a characteristic color of a variety of Teflon called Viton, V-I-T-O-N. These black seals are Buna rubber, probably Buna 70. Generally oil resistant, they're not very good for heat. The reason for Viton seals is that Viton's good for upwards of 400 degrees Fahrenheit and resistant to most chemicals. And especially in an old vehicle, there's going to be exposure to grease, oil, fuel, antifreeze, all kinds of chemicals. Those chemicals do bad things to just ordinary Buna rubber. They can eventually soften the seals and cause the oil to leak out. So for automotive purposes, if you can, get bearings with Viton seals. This is an alternator. It's going to get hot. There's engine heat nearby. That's a better seal because it's made of more temperature-resistant material. And in addition to the cautions of never ever dropping that bearing, never put that bearing in an assembly and drop the assembly. The same thing will happen. Never hit the shaft with a hammer. That immediately will damage the bearing. So, two main takeaways. Never put impact force on a bearing of any kind. And never ever, unless it's unavoidable, press a bearing race on a shaft or in a housing. KBYP did it.